Okay, so we'll start off by demonstrating the basics of setting up a static analysis, loads, constraints, contacts, and just look at some of the post-processing tips and tricks. So for many of this will be familiar, maybe just a couple of bits to pick up on before we delve into some more detailed examples. Okay, so here it is, our simple hook. It's a very familiar example if you've ever gone through any of the optimization tutorials. And what we're going to do in this example is apply a 2 kilonewton load to this loading pad at the bottom, fix these 4 pads, and we're going to define contact between the surfaces, run it, and evaluate the stresses. So let's go through that. So the key thing inside Design Studio we want to be working at today are display, analysis, and post. The optimization tabs will be left well alone today. That's not typical for most of the demos we do. Okay, so first of all, I'm going to define some constraints, and if you're looking to define SPC constraints inside the Design Studio interface, you'll find those tucked away inside the Grid Components Sets interface. So I can go to here and then create new. Everything inside Design Studio has access via these icons. I'm just going to do fixed ends. So here you can see single point constraints, SPCs as they're known, which are put onto each of the nodes. And so I can go next, and here I can choose to pick by feature angle, so I can simply select the nodes on these ends. And then the way the interface works in Design Studio is you make your selection, and then from the current selection of grids that you have, you choose what you want to do with them. So we'll say I would like to fully constrain, so all of the 6 degrees of freedom I'd like to constrain, and I'll choose set. It's actually a little bit of an unusual approach. You can't now modify those fixings in a sort of a traditional way. The way it works, if you want to make a change to these, you have to work with your selection of grids and then either clear and redefine or modify in this way. So if I take an example here, say for example I wanted to remove the X constraint on these nodes, there's no way of doing it by just changing the setting. I have to actually show only one. So what do I want to do with attribute 1, which is your X displacement, and then I would clear that. And you can see here now I have remaining the 2 to 6, and I can put it back like so. So it's a logic of make a selection, choose the constraint degree of freedom you want to work with, and then choose either to clear or add, depending on what's present on the node. Okay, so with those set, I can finish that. And you'll also notice some other little tips and tricks in Design Studio are the nodes on screen, you can see are actually still selected. So one of the things I do as a habit very much in Design Studio is I right click and choose clear all. So that's taken away my selections. It's important for the next step, which is to define my static loads. So here I'm going to go to static loads, new, and I'll put 2 kilonewton force as my title. You see here we've got options for forces and moments and pressures, and SPCD is then an enforced displacement as a further option. But additionally, you've also got gravity loads to apply as acceleration fields, thermal structural loads, so temperatures that would relate to some expansion or contraction of material to create strains, centrifugal loads, and then lastly you can generate load combinations, so you can mix different loading components together. So in this case we're just going to apply a force, and what we'd like to do is apply a total of 2 kilonewtons on this load pad here. So what I'm going to do, I can choose load direction and magnitude, or just vectors, so I'll stick to vectors. My direction is negative y, and so what I'll do is I'll choose all in group, and then I can pick on this part. So if you look at this, I've got a selection of 1,190 grids. What I'm going to do is define minus 2 kilonewtons. And I want to just distribute that across all of these nodes, so I divide by the number of grids I've got. That's the technique that you approach in Design Studio. Once I do that, you'll see that if I zoom in, each of the nodes has got 2,000 divided by 1190, so that's a total of 2 kilonewtons. Okay, so with that finished, again, I just like my habit of selecting none. Next, I'd like to define some contact. So at the moment, if I try and solve this, there's no automatic knowledge of the contact between our green and red and our blue and red parts. So I need to define some contact, and that falls under the contact data section here. And what I can do is define it. In this case, I'll define the contact groups just by their properties. There are several available. We can do by element, by material reference, or by property. So in this case, we'll use by property, and I'll create 3 groups very quickly here. So a hook group, like so. A pins group, pick off screen, and then a load group here. So with these in place, I can now set about defining my contacts, and we'll discuss in the next example a bit more detail about contacts and how they work. But if we take a look at this surface here, you can see we've got a discontinuous mesh refinement between the surfaces, and that's no problem to deal with in Genesis. But one of the tips there on something like a cylindrical surface, where you'll end up with some penetration and some gaps, is we can tell the contact algorithm to just ignore that initial offset in surface distance and start as though the surfaces are just simply in contact. So let's do that first of all. We'll define this load pad to hook. So a contact surface pair where iterations will take place is a BC pair. So I'll do load to hook. We'll put the load as the slave, the master as the hook. Because I'm using parts, I'm actually going to put a sensible search distance, just 1 millimeter, so that's just surrounding the surface. Because by using parts, otherwise we've got the potential of surfaces here may end up contacting all the way up here, which are really not applicable. So it just saves a bit of searching and testing to put a sensible number there. And then I mentioned about the initial gaps and penetration around this cylinder. We can choose to ignore any of that by choosing the ignore option, which I will do, and then we'll define a friction coefficient of 0.2. The next contact will be the pins to hook. Similar contact type. This time we'll make the pins the slave. We'll keep the hook as the master this time. A similar rationale for the contact and also for friction. So with the contacts defined, what I need to do now is generate a contact group so that they're all used at the same time. So we have what's called a union of contact pairs. I can do all contact. I can pick those and group them together. And then the last thing I need to do to be able to do a contact is to specify control parameters for the nonlinear solving of the contact. So this is in fact a remarkably straightforward option, is you just leave it empty, which will be 25 iterations as a default setting. If you do need more iterations for convergence, then that's straightforward to just put a number in there. So that's our contact definition data defined. We've got loads and constraints. So now we want to create our load case where we bring it all together. So if I do vertical load as a name, and here you can see as we'll be working our way through these today, statics is the first one in our list, the most commonly used, I would say. We'll choose that. And then this is just straightforward step-by-step. Choose fixed SPCs for constraining the part. We'll choose all contact, and our control parameters are here. Next, we can define our load. And as you saw in the static load interface, there were several different types to be used, and you can see here how you can select those. Note, we'll come back to it later in our examples, but we also have our bolt preload load case that's available if we want it in this stage. Now here we're looking at a solid mesh, so what we really care about are the surface stresses, and those are best represented for solids using the grid stress output. If you're familiar with other codes that often will store the element result data in terms of centroidal stresses and also corner stresses, in Genesis it's stored somewhat differently. The element stress is the centroidal stress here, and then the grid stresses for the solids are actually reported as a separate output. So it's useful and in fact very important if you're doing solid model analysis to request that output. Lastly, we'll do contact pressure here, so we can review the contact pressure on the surfaces as an output. We'll finish that, and all being well, I can run. You'll see here the contact iterations converging. As always with tutorials, this has worked fine. As mentioned, I'll go to one that doesn't in a moment so we can learn a bit more about it. So we can pick up our results via the solver console. For anybody that's not sure, if you didn't import via that console, you can of course import results here via the punch output, where you can choose the filtering of output. You can choose particular components you want to import. That's often very useful if you've got very large results data, and also selected load cases can be chosen to import if you have large results data. That's a useful tip to keep in mind. Okay, so that's run, so let's take a look at our results. Here we've got our displacements. Reassuringly, first demo has actually worked without error, which is always good. And you can see the contacts are just holding tightly. Now, it's important to understand here on the post-processing how these two modes that are described as filled elements and filled contours work when we look at the results we've got in terms of stresses. So generally the rationale inside Design Studio is filled elements refers to element-based results. So if I look at that and I look at solid stress, for example here, I can see these are my element-based results because they're solid element stresses. Filled elements means they're colored on the elements. So those results I'm looking at as I work my way along. I've got a maximum here of 9.8 and 10.4 there is the peak. So 10.4 is a centroidal stress in this corner. If I choose to then plot a filled contour, what that's going to do is that's actually going to smooth the results from center to the grid locations. And actually what you find is the result will drop. So we've gone from 10.4 to 10.1 to get these nodal values that I can now look at on the grid. And this is really important when you're looking at solid stress analysis, because what you really want is the surface stress, grid stresses exactly as they are calculated, and that's where this grid stress component comes in. And you can see that becomes quite significant as a result. If I choose here, now my peak stress is actually nearer 14 megapascals because that's the correct surface stress evaluated for the solid. So a really important step that when you're doing a solid element analysis in Genesis. Okay, in terms of how you review the results, you've noticed there I can just hover over anything to review. I can grab a load and it will print the values I've selected. And additionally, if I want to learn a little bit more about it, I can also add some tags to my results. So I can look here, for example, I'd like to look at the maximum value in my result. And you can see here that's actually highlighted it nicely for us at 13.76 megapascals. Okay, the last thing to show on this working example is our contact pressures. You can see here These are just plotted on the faces where contact is defined, and you can see the distribution of contact as you'd expect. And similarly here, we have our contact pressures as you'd expect to see. Okay, so that's the mechanics of the process, and that all works. But when it comes to contact analysis, what happens when it doesn't work? So let's take a look at that for a moment. So by default, when you're solving in Genesis and you've built a model, and very often the case is you may have just missed something, a simple SPC or something, rather than it being anything too sinister in terms of your contact model. But if it doesn't converge, you can't see anything by default in Genesis. It just simply will say fail to converge, and you can't see your answer. But there are some tips to work around that, and a real key one here is a parameter called, excitingly, IPRM12. You can only dream of these names. And if we take a look at that, we can see how we can learn more what's going on. So if I just close that model, and I've got this rather Blue Peter style prepared example whereby I think I've set this up right. I'll try and solve it, and we'll see what happens. Okay, so here you can see the iterations progressing, but unlike the nice tutorial, there's this upsetting sight that as you see the numbers go down, then they all of a sudden start to go up again and oscillate, and oh, there we go, we've gone up. And there's that upsetting sight at the end. I've got no convergence. I've got a fatal error, and the fatal error will simply be saying it didn't work. So in such a case, you haven't got an output file and you can't see any more. So what you do is you simply go to your analysis control, and you go to your advanced menu here, and you can sneak in to this other parameters option. You can add in the option we want. So it's IPRM12 and define a value of 13. At this stage, I think I've never defined anything other than 13. They're just output flags. So these are the ones to do. Make sure I've done that right. IPRM12. IPRM12, good. So with that defined, I can solve this again. And all being well this time, I can actually understand what's going on. As you see, I've not done anything to actually fix the problem at this stage. I'm just going to solve and get output. In many ways, I would urge a little bit of caution as you do it, but it's not uncommon for me to just always include that option from the start. It means that right from the debugging stage, I can check. But if you do include it, just be aware that you do need to look that you have actually got convergence before you report any results that you'd be wanting to believe. So now I've got my output, I can look at that and see if we can identify what's wrong with the model. Okay. Yeah, that's just not constrained. So you can see here, my pins are not constrained as I'd expect them to be. If I look at my load case, you can see these pins should be fixed. So it's an easy fix, just fix it. And it's often the case with Genesis is convergence is actually is very good. So it's often the case that the setup, something you'd see as a reported singularity in a non-contact solve, is just going to flag that non-convergence unless you can see it some way. So you can see straight away we've got our result. And we're good to go. And that's all working. Okay. So that it's probably the biggest tip for anybody doing contact in Genesis, I think, is to support that. Now, if you are quite satisfied with your model, sometimes there are just difficult contacts. There's lots of contacts in real world complex models with lots of assemblies, preloads, and so on. And if you're encountering convergence problems in such models, then there are some other tune-ups you can do. And basically, when it looks for the convergence of all the contact surfaces, it's looking for a sort of a limit of change or between the forces and displacements in the surfaces. So if by eye it's looking very good, but you're just a little concerned you can't get convergence, you can relax these two parameters here, RPRM 10 and 11, and these are controlling the displacement and force convergence tolerances. So the defaults here are 1e minus 4 and 5e minus 3. So a typical start point is to actually reduce those, or relax those, I should say, by increasing the number by a factor of 10.